What if every decision you've ever made, and every one you didn't, still exists somewhere out there? What if there are other versions of you, living out the lives you sometimes imagine, in worlds just slightly different from this one? From the tiniest quantum events to the birth of entire galaxies, nature may be creating new worlds constantly. Infinite reflections branching from every possibility. If that's true, then everything you've ever done, every path you didn't take, may still be unfolding somewhere, right now. Tonight, we're going to explore one of the most fascinating ideas in all of science, the theory of parallel worlds, and the growing evidence that reality might be far bigger, stranger, and more interconnected than we ever imagined. We'll travel from quantum experiments to cosmic inflation, from hidden dimensions to black holes, and discover why serious scientists are asking whether our universe might just be one of many. If you enjoy drifting through ideas that challenge what we think we know and help you see the universe with fresh eyes, you're in the right place. Feel free to close your eyes, breathe deeply, and let your imagination wander through the infinite possibilities that might be unfolding all around you. Also, I'd love to know where you're listening from tonight. Comment your time and location. Before we begin our journey across the multiverse, let's begin. Right now, as you listen to this, countless versions of you might be doing something else, living slightly different lives in slightly different worlds. It sounds like science fiction, but some of the most serious physicists in modern science believe it could be true. The idea of parallel worlds, or the multiverse, has quietly evolved from speculation to a legitimate field of theoretical physics. And the story begins with a question that still puzzles scientists today. Is the universe we see the only one that exists? For centuries, humans assumed there was just one reality, one cosmos containing everything. But in the 20th century, quantum physics began to challenge that assumption. In laboratories around the world, researchers discovered that particles, the building blocks of everything, don't behave like solid, predictable things. They exist as probabilities, overlapping in multiple possible states until they're observed. This strange behavior was first revealed in the early 1900s through experiments like the double-slit experiment, which showed that particles of light and matter can act like waves, passing through two openings at once and interfering with themselves. It was as if a single particle could exist in multiple versions of reality simultaneously. Physicists like Niels Bohr and Werner Heisenberg tried to explain this mystery with what became known as the Copenhagen interpretation, the idea that a quantum system doesn't have definite properties until it's measured. Reality, in this view, is not fixed. It's only decided when we observe it. But in 1957, a young Princeton physicist named Hugh Everett III proposed something revolutionary. He suggested that when a quantum event occurs, the universe doesn't choose just one outcome. It branches into all possible outcomes. In one branch, an electron goes left, in another, it goes right. Both outcomes happen, just in separate, non-communicating realities. Everett called this the many worlds interpretation of quantum mechanics. In his view, every quantum event spawns countless new universes, each as real as our own. What looks like randomness is simply us experiencing one thread of a much larger tapestry, a vast, branching multiverse. At first, his idea was dismissed as too radical, even absurd. But over time, as quantum theory continued to defy common sense, Everett's interpretation started to gain respect. Physicists like Bryce DeWitt helped popularize it, and thinkers such as Max Tegmark, Sean Carroll, and David Deutsch began exploring its implications. What's remarkable is how this theory links the tiniest particles with the grandest scales of the cosmos. If quantum mechanics allows for multiple realities at the microscopic level, could the same principle apply to the entire universe? Could the cosmos itself be one of many, each with different laws of physics, histories, and outcomes? Cosmologists like Alan Guth and Andre Linde think that might be the case. Their work on cosmic inflation, the rapid expansion that followed the Big Bang, suggests that new universes may be constantly forming, each beyond the reach of our telescopes. If true, the multiverse isn't just possible, it might be inevitable. In this documentary, we'll explore the evidence and ideas behind these extraordinary claims, from quantum mechanics and string theory to cosmic inflation and consciousness. We'll see how multiple lines of science seem to point toward one astonishing conclusion: that reality could be much larger than we ever imagined. A vast ocean of worlds, with ours as just one wave upon its surface. And as we journey through these theories, one question will guide us. If parallel worlds are real, what does that mean for us? For choice, for consciousness, and for our understanding of existence itself? At the heart of modern physics lies a puzzle so strange that even the scientists who discovered it could barely believe what they were seeing. It's a mystery that began not in the vastness of space, but in the smallest experiments ever performed. Experiments that seem to suggest that reality changes when we look at it. In the early 20th century, researchers studying light noticed something peculiar. When they sent particles of light, photons, through a pair of slits in a metal plate, they expected to see two lines appear on a detector behind it, just as tiny bullets would behave. But that's not what happened. Instead, the light created an interference pattern, a series of bright and dark bands, the signature of a wave passing through both slits simultaneously. When scientists tried this with single particles, firing them one at a time, the same thing occurred. Over time, they built up an interference pattern. Each individual particle somehow seemed to interfere with itself, as though it had traveled through both paths at once. The question was unavoidable. How could something be in two places at the same time? Then came the strangest part. When the scientists decided to measure which slit the particle actually passed through, the interference pattern disappeared. The act of observing changed the outcome. The particle now behaved like a single bullet, taking only one path, as if the universe itself had waited for someone to look before deciding what to be. This was the birth of one of the most profound mysteries in all of science, the measurement problem of quantum mechanics. What causes a particle's many possibilities to collapse into one reality? And what exactly does observation mean? Physicists like Niels Bohr and Werner Heisenberg argued that the act of measurement, even by a simple detector, forces nature to make a choice. In their Copenhagen interpretation, a quantum system exists only as a cloud of probabilities until it's observed. In other words, reality is not definite until it is measured. But this idea troubled many scientists, including Albert Einstein, who famously objected, "I like to think the moon is there, even if I'm not looking at it." Einstein believed the universe must exist independently of observation, that something deeper, something hidden, was guiding these outcomes. Yet decades of experiments have failed to find those hidden variables. Instead, each test of quantum theory has confirmed its bizarre predictions. Nature truly behaves probabilistically. To make sense of this, some physicists began to wonder, what if the wave of possibilities never actually collapses at all? What if instead all outcomes happen, but in separate, parallel realities? In one, the particle goes left. In another, it goes right. In one world, you observe it behaving as a wave. In another, as a particle. This idea would later form the basis of Hugh Everett's many worlds interpretation, which we'll explore in the next chapter. But even before Everett, the seeds of the multiverse were already there, hidden in the equations of quantum mechanics themselves. Each time a quantum event occurs, it doesn't seem to destroy the other possibilities. They're simply inaccessible to us, branching away, existing alongside our own. And if this applies to every particle, every atom, every decision, then perhaps the universe isn't a single unfolding story, but an endless library of possibilities, with every page written somewhere in the fabric of reality. What quantum physics revealed is unsettling, yet beautiful. It shows that the universe is not fixed, but fluid. Not one world, but perhaps many. each emerging from the dance of observation, chance, and fundamental laws we're only beginning to understand. By the mid-1950s, quantum physics had already transformed science. But it had also created an uncomfortable paradox. Every experiment worked perfectly, every prediction held true, and yet no one could explain what was really happening. Was reality choosing just one outcome when we observed it? Or were we seeing only one thread of something much larger? In 1957, a 27-year-old Princeton graduate student named Hugh Everett III offered an answer so bold that few took him seriously at first. His doctoral thesis proposed what he called the relative state formulation, an idea that would later become famous as the many worlds interpretation of quantum mechanics. Everett argued that the so-called collapse of the wave function, the moment when a quantum system seems to choose a single state, never actually happens. Instead, he suggested, every possible outcome of a quantum event actually occurs, each in its own distinct universe. Imagine tossing a quantum coin. In our world, it might land heads, but in another, equally real branch of reality, it lands tails. Both universes continue forward, unaware of each other, each containing a version of you who witnessed one outcome. It was a simple but radical idea. The universe never decides, it divides. This interpretation didn't require observers to have special powers, nor did it depend on mysterious collapses of probability. The equations of quantum mechanics, Everett said, were already complete. They just had to be taken literally. To illustrate the weirdness of quantum superposition, Erwin Schrödinger, decades earlier, had created a thought experiment that became legendary. He imagined a cat sealed inside a box with a tiny amount of radioactive material. If the atom decayed, it would trigger a mechanism releasing poison, killing the cat. If it didn't decay, the cat would remain alive. According to quantum mechanics, until someone opens the box, the atom exists in both states, decayed and undecayed, meaning the cat is both alive and dead at the same time. For most physicists, this was absurd, a paradox meant to show the limits of quantum theory. But Everett's interpretation took it at face value. He argued that when you open the box, the universe splits. In one branch, you see a living cat. In another, a dead one. Both outcomes are real, each unfolding in its own separate world. At first, Everett's idea was ignored, even ridiculed. His advisor, John Wheeler, admired his brilliance, but struggled to convince the wider community. Everett eventually left academia and went on to work in defense research, never fully seeing how influential his idea would become. It wasn't until decades later, in the 1970s, that physicist Bryce DeWitt revived and popularized Everett's theory, giving it the name many worlds. Since then, it's attracted serious attention from respected thinkers like David Deutsch at Oxford, Sean Carroll, and Max Tegmark at MIT, scientists who see it not as fantasy, but as a logical consequence of quantum mathematics. According to the many worlds view, every quantum decision, every particle spin, every photon path, every human choice continually branches reality into countless parallel versions. In this vast structure, known as the universal wave function, all histories coexist. There's a universe where you chose a different career, one where Earth never formed, and another where you never existed at all. Of course, we can't observe these other branches directly. They don't interact with ours, which is why the idea remains theoretical. But mathematically, the many worlds interpretation is elegant. It removes the randomness of quantum collapse and replaces it with deterministic branching. The universe doesn't roll dice. It explores every possibility. As strange as it sounds, some physicists now consider this the most straightforward reading of quantum mechanics. There's no special role for observers, no hidden variables, just a vast, constantly dividing multiverse. It's an extraordinary vision of reality, a cosmos not of one timeline, but of infinite histories, all real, all happening, forever branching from a single origin. And if that's true, then the mystery of quantum physics isn't that particles behave unpredictably. It's that we experience only one version of a universe that's far richer than we can ever perceive. So far, we've seen that parallel worlds might exist both at the quantum scale, where particles branch into multiple realities, and at the cosmic scale, where bubble universes form in an ever-expanding multiverse. But the story doesn't end there. Theoretical physics suggests that reality may be far richer than the 3 dimensions of space and one of time that we experience daily. This is the realm of string theory, a mathematical framework that attempts to unify all fundamental forces, gravity, electromagnetism, and nuclear interactions, into a single, elegant theory. According to string theory, the smallest building blocks of the universe aren't point-like particles, but tiny vibrating strings. Each vibration corresponds to a different particle, much like different notes on a violin string produce different sounds. The theory predicts the existence of up to 11 dimensions, many of them hidden, curled up so tightly that we cannot directly observe them. Some physicists suggest that these extra dimensions could provide a playground for parallel realities. In a concept called brain cosmology, our universe exists on a 3-dimensional brain, floating in a higher dimensional space. Other brains could exist nearby, other universes invisible to us, occupying the same higher dimensional space, but separated along dimensions we cannot perceive. Occasionally, theoretical models propose that these brains could collide. Such collisions might release enormous energy, perhaps even causing events similar to the Big Bang, giving birth to new universes. In this view, universes are not isolated, but part of a vast multidimensional structure, a cosmic ecosystem where creation is ongoing. Leading physicists in this field include Edward Witten, one of the pioneers of string theory, and Brian Greene, who has popularized the concept in books and documentaries. Their work has inspired the idea that hidden dimensions may not just be abstract mathematics, but a real arena in which parallel worlds could exist. String theory also suggests that the physical laws in these parallel realities might differ dramatically. The strength of gravity, the types of particles, even the number of time dimensions could vary from universe to universe. Some universes might be unrecognizable, yet still follow the same underlying mathematical rules that govern everything we know. While we currently lack experimental proof of these extra dimensions, certain efforts aim to detect their effects indirectly. Particle accelerators like the Large Hadron Collider, LHC, search for evidence of higher dimensional phenomena, and cosmologists study subtle patterns in the cosmic microwave background for hints of brain interactions. The implications are profound. If hidden dimensions exist, the universe we perceive is only a small part of a far more complex reality. Parallel worlds could be not only possible, but spatially adjacent, intertwined with our own, yet forever inaccessible to ordinary perception. In essence, string theory expands the multiverse concept beyond quantum branching or cosmic bubbles. It introduces a new frontier, a universe that may be infinitely richer than we imagined, with dimensions and realities layered upon one another like pages in a cosmic book, each waiting to be explored. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment that would challenge the foundations of quantum mechanics. They described a situation in which 2 particles could become mysteriously linked, their properties perfectly correlated, no matter how far apart they were. Einstein called it spooky action at a distance. Today, we call it quantum entanglement. When 2 particles become entangled, their quantum states are no longer independent. Measure one, and you instantly know the state of the other, even if they're light years apart. This happens not because a signal travels between them, but because they share a single unified quantum state that spans both locations. This isn't speculation. It's been confirmed repeatedly through experiments. In 2015, a series of loophole-free experiments led by physicists such as Ronald Hansen at Delft University demonstrated entanglement beyond any classical explanation. More recently, entanglement has been tested over hundreds of kilometers through satellites like China's Mischius. showing that quantum connections can stretch across space. But what does this have to do with parallel worlds? In the many worlds interpretation, when two entangled particles are measured, each possible outcome occurs, but in separate branches of reality. The entanglement doesn't vanish, it extends across those branches, maintaining a kind of quantum consistency between them. Some physicists, like David Deutsch and Lev Weidman, suggest that entanglement could actually be evidence of multiple realities interacting at the quantum level. In this view, what we call entanglement might not be a mysterious connection through space, but a reflection of parallel branches remaining synchronized across universes. Each time a quantum decision occurs, the multiverse splits, yet the correlations between outcomes remain perfectly balanced, as though nature keeps all its books aligned. There's another intriguing connection here, the ER-EPR conjecture, proposed by physicists Juan Maldacena and Leonard Susskind. It suggests that entangled particles might be connected through microscopic wormholes or Einstein-Rosen bridges. If true, entanglement and space-time geometry are two sides of the same coin. And if wormholes can exist between entangled particles, could they also connect different universes? While that remains speculative, it points to a unifying idea. Quantum entanglement might not just connect particles, it could weave the very fabric of reality, linking not only points in space, but entire branches of the multiverse. In laboratory settings, researchers are already exploring entanglement swapping and quantum teleportation, where the state of one particle is instantly transferred to another. These experiments don't send matter itself, but information across entangled systems. It raises a tantalizing question. If information can cross quantum boundaries, could consciousness, or the structure of reality itself, also be entangled across universes? We don't yet know the answer, but each new discovery brings us closer to understanding that entanglement may be more than a quantum curiosity. It might be the signature of a deeper reality, one where separation is an illusion and all things are connected, not just across space, but across the boundaries of worlds. The idea of parallel worlds may sound like science fiction, but over the past few decades, a number of discoveries have quietly given it scientific weight. While none are definitive proofs, together they paint a picture of a universe that might be far more complex and interconnected than we can currently see. Let's start with the cosmic microwave background, or CMB, the faint afterglow of the Big Bang. This radiation fills all of space, a remnant of the universe's earliest moments. When scientists first mapped it in detail using satellites like COBE, WMAP, and Planck, they expected a nearly uniform pattern of temperature. But what they found were small irregularities, and in one region, something far stranger. A large, unusually cold region known as the cold spot has puzzled cosmologists for years. Some suggest it might be the imprint of a massive void, a region of space with fewer galaxies. But others, like Laura Massini-Houghton from the University of North Carolina, have proposed a more radical explanation, that the cold spot could be the gravitational imprint of another universe, one that collided with ours in the distant past. Her hypothesis is bold, but it aligns with predictions from cosmic inflation, that our universe could have formed alongside others, with occasional interactions at the boundaries. If true, the CMB might contain fossil evidence of another reality brushing against our own. Other hints come from quantum physics itself. The double-slit experiment and entanglement continue to defy classical explanation, suggesting reality behaves probabilistically at a fundamental level. If the many worlds interpretation is correct, these probabilities represent real outcomes across many universes, a conclusion supported mathematically by the equations of quantum mechanics. Then there's the fine-tuning problem, the fact that the physical constants of our universe appear delicately balanced to allow for stars, planets, and life. The strength of gravity, the mass of the electron, and the cosmological constant all fall within extremely narrow ranges. If any were slightly different, matter might never have formed, or the universe might have collapsed moments after the Big Bang. One explanation is pure coincidence. Another, offered by cosmologists like Max Tegmark and André Linde, is that we live in one of many universes, a rare bubble where conditions happen to permit life. This is often called the anthropic principle. We observe this universe because it's one of the few where observers like us can exist. Even particle physics hints at hidden realities. The mysterious dark matter and dark energy, which make up over 95% of the universe, remain unexplained. Some researchers speculate that dark matter might represent matter from another dimension or parallel universe, gravitationally interacting with ours. Theoretical models like the brain world scenario in string theory support this idea, suggesting that gravity could leak between universes. While we don't yet have direct evidence, the convergence of these clues, quantum anomalies, cosmological patterns, and unexplained cosmic components, suggests that our universe might not be an isolated system. Instead, it could be part of a grander multiverse, where each universe influences the others in subtle, measurable ways. The challenge for science is clear. How do we test such a vast idea? New generations of telescopes and particle accelerators may one day provide answers, revealing traces of collisions, gravitational waves, or higher dimensional effects. Until then, we stand at the edge of knowledge, looking out into the cosmic darkness, aware that what we see may be only a single reflection of an infinite reality. If the multiverse is real, if every quantum decision branches reality into countless possibilities, then somewhere out there, another version of you is making a different choice right now. In one world, you chose a different career. In another, you never met the people who shaped your life. In countless others, you may never have been born at all. It's a strange, humbling thought that every decision, no matter how small, might echo through an infinite network of alternate selves. The many worlds interpretation of quantum mechanics, first proposed by Hugh Everett, implies that each possible outcome of an event becomes real in its own branch of the universe. From a quantum perspective, there is no single continuous you. Instead, there is a vast family of versions, each diverging with every choice, each as real as the one you experience now. This idea forces us to reconsider free will. If every possible decision is made somewhere in the multiverse, what does choice even mean? Some philosophers suggest that what we call free will is simply the experience of navigating one particular branch of a much larger reality. You still make choices, but every other version of you does too, in parallel. The act of choosing doesn't eliminate other possibilities. It simply places your awareness within one of them. There's something both unsettling and liberating about that idea. It means that no possibility is truly lost, that all outcomes, even the ones we regret or dream about, still exist somewhere, unfolding in their own timelines. At the same time, it reminds us that our own experience, this single thread of consciousness, remains uniquely ours. Some thinkers, like Max Tegmark, describe this structure as the level 3 multiverse, where quantum branching creates infinite versions of reality. Others, like Sean Carroll, see it as a natural consequence of quantum physics, not a philosophical speculation. Carroll once put it simply, the many worlds interpretation is just quantum mechanics, taken seriously. But beyond physics, this idea touches something deeply human, our sense of meaning and identity. If there are infinite versions of you, what defines you? Is it your memories, your consciousness, or just the particular path your branch of reality has taken? Neuroscience tells us that memory and identity are emergent patterns in the brain, stable, but constantly changing. If consciousness is tied to quantum processes, as some researchers like Roger Penrose and Stuart Hameroff have suggested, then perhaps even awareness itself has quantum properties, branching and evolving across realities. Of course, none of this means we can visit these other worlds, or even sense them. Each branch exists independently, isolated by decoherence, the process that prevents interference between parallel states. But the implications remain profound. If the universe continually creates infinite versions of reality, then existence itself is not a single story. It's a vast library of experiences, every one of them real to someone, somewhere. And your life, right now, is one page among countless others, brief, fragile, but no less meaningful for it. The multiverse doesn't make your choices meaningless. It makes them precious. Because out of infinite possibilities, this is the one you're living. This moment, this version of you, this tiny corner of a vast cosmic sea. Among the strangest objects in the universe, none are as mysterious or as revealing as black holes. For decades, scientists thought of them as the ultimate voids, regions of space where gravity is so intense that nothing, not even light, can escape. But modern physics has shown that black holes may not be simple cosmic dead ends. They might be gateways, linking our universe to others. To understand why, we have to look back to the 1970s, when Stephen Hawking made one of the most groundbreaking discoveries in theoretical physics. He showed that black holes aren't completely black. Through a subtle quantum process near their event horizons, the boundary beyond which nothing returns, black holes slowly emit radiation, now known as Hawking radiation. This meant black holes could eventually evaporate, releasing their mass back into space over unimaginable timescales. But this discovery also revealed a paradox. If a black hole eventually disappears, what happens to the information about everything that fell into it? Quantum mechanics insists that information can never be destroyed. Yet general relativity seemed to suggest it could vanish forever inside a black hole. This puzzle, the black hole information paradox, has driven some of the most profound debates in physics for half a century. And one of its possible solutions leads directly to the idea of parallel universes. According to one line of thinking, when information enters a black hole, it might not be lost at all. Instead, it could be transferred or encoded in a new region of space-time, effectively giving rise to a new universe. In this model, every black hole could be a kind of cosmic seed, a tunnel through which a new universe forms on the other side. Physicists, such as Lee Smolin, have explored this idea through what he calls cosmological natural selection, the hypothesis that universes reproduce through black holes, each new cosmos emerging with slightly different physical constants. In that sense, our universe could be the offspring of another, born through a black hole in a parent universe. Meanwhile, theories in string theory and quantum gravity suggest that black holes might not destroy information at all, but rather store it in a two-dimensional form on their surfaces, an idea known as the holographic principle, developed by Gerard 't Hooft and Leonard Susskind. If the universe itself operates holographically, then perhaps all of reality, including the possibility of other universes, is encoded on vast cosmic horizons we cannot yet see. And then there's the even wilder idea, the ER-BIAS-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, which links wormholes, Einstein-Rosen bridges, with quantum entanglement. If entangled particles are connected by microscopic wormholes, then maybe black holes, the extreme version of that idea, could connect entire universes. In that case, a black hole might not destroy information, but simply move it elsewhere, across a bridge to another world. Though these ideas remain theoretical, they represent the frontier where quantum physics, general relativity, and cosmology meet, and they suggest something extraordinary, that black holes may not just mark the ends of stars or galaxies, but the beginnings of new realities. Every black hole could be a doorway, silent, invisible, and unreachable, leading to another universe where new laws of physics, new forms of matter, and perhaps even new versions of space and time unfold. If true, then our own Big Bang might have been the birth cry of a black hole from another cosmos. And right now, somewhere in the depths of space, black holes in our own universe could be giving birth to others, continuing the endless cycle of creation, destruction, and rebirth across the multiverse.